Now we're starting with metals. Some general properties of metals include that they are good conductors of heat and electricity. They have high densities and high melting point and boiling point. Also, metals are malleable, that is, their shape can be changed, and ductile, that means they can be drawn into wires. Now, why are metals malleable? The structure of metals, the metallic lattice, is like this. There are positive ions, positive cations, and a sea of delocalized valence electrons. Now, these layers can slide over each other. That is why they can change shape. Alloys are a mixture of a metal with one or more other elements. For example, brass is an alloy that is a mixture of copper and zinc. Now, properties of alloys. Alloys are more resistant to corrosion than their respective elements. Also, alloys are stronger, that means less malleable. Why are alloys less malleable? In alloys, for example, copper and zinc, copper has the atomic number 29 and zinc has 30. That's why the radii of copper and zinc might vary. Therefore, their structure would be something like this. Now, when pressure is applied or force is applied, the layers won't slide past each other because there is an obstruction in the path. Therefore, they are stronger and less malleable. The reactivity series of metals. There is potassium, sodium, calcium, zinc, this is the reactivity series, potassium being the most reactive and platinum being the least reactive. So, when we consider the reactions of these metals with water, or water, steam, oxygen, and acids, we have to keep this reactivity series in mind. With water at RTP, room temperature and pressure, sodium, potassium, and calcium have a very fast reaction or violent. Magnesium has a slow reaction. When magnesium metal is put in water, apparently there is no reaction, but slowly bubbles of hydrogen gas are produced just on the outside of the metal. After magnesium, there is aluminium. From aluminium till platinum, there is no reaction with cold water, with water at room temperature. With cold water, again potassium, sodium and calcium have a fast and violent reaction, while magnesium till platinum have no reaction. Next is with steam. Potassium till iron, that is potassium, sodium, calcium, magnesium, aluminium, zinc and iron, they react with steam to form metal oxide and hydrogen gas.
Yes, ma'am.
However, from lead till platinum, there is no reaction. With oxygen, potassium till zinc react at room temperature. Iron till hydrogen react on heating. Copper reacts at room temperature. While mercury till silver react on heating. And gold and platinum do not react with oxygen. These reactions produce a metal oxide. Lastly, there is the reaction of metals with acid. Reactive metals react with an acid to produce salt and hydrogen gas. From sodium till magnesium, the reaction with an acid is fast and violent. From aluminium till lead, it is slow. And from hydrogen till platinum, there is no reaction. Displacement reaction of metals. In the displacement reaction of metals, the upper one metal in the reactivity series displaces the lower one metal ion from its compound. For example, if we have iron plus copper sulfate, iron being higher in the reactivity series will displace copper, forming iron sulfate and copper. The ionic equation for this reaction will be made using the ions that are changing, whose valency is changing. Iron is becoming iron 2 plus and copper 2 plus is becoming copper. So that's why we'll use iron plus copper 2 plus, producing iron 2 plus plus copper. These are aqueous and these are solid. One more reaction is the thermal decomposition of metal carbonates and metal hydrogen carbonates. Potassium and sodium metal carbonates, potassium and sodium carbonates are stable to heat and they are not decomposed, while calcium till copper carbonates are decomposed on heating. And carbonates of mercury, silver, gold and platinum, that is Hg till Pt, do not exist. Heating, for example, magnesium carbonate would produce magnesium oxide plus carbon dioxide gas. And similarly, if a metal hydrogen carbonate is heated, a metal carbonate, water and carbon dioxide gas are produced. For example, sodium hydrogen carbonate produces on heating sodium carbonate plus carbon dioxide gas plus water. The next topic is the extraction of metals from their ores. The reactivity series will be potassium, sodium, potassium, magnesium, aluminum, zinc. We have carbon over here. This is carbon and this is hydrogen. Now, to extract a metal from its ore, from potassium till aluminum, electrolytic reduction is used. That is, the ore is heated to form to convert it to molten form, and then it is electrolyzed to form the pure metal. From zinc till platinum, chemical reduction is used. Chemical reduction means using another element to displace the metal that has to be extracted. For example, if it's from zinc till lead, carbon is reacted with the ore, carbon displaces the metal, the metal is formed and a compound of carbon is formed. Or if the metal is from copper till platinum, then hydrogen is used to displace the metal from its compound. For mercury till platinum, thermal reduction can also be used. That is, if the ore is heated, the metal can be obtained by decomposing it. Now we're doing the extraction of iron from its ore. The ore of iron is hematite. That is Fe2O3, iron 3 oxide. Iron is extracted by chemical reduction, and the reducing agent being used is carbon, called coke. This reaction takes place in a blast furnace. In the blast furnace, which is a large container where the temperature is maintained at 1900 degrees Celsius. Calcium carbonate, that is limestone. Carbon, that is coke. And iron 3 oxide, that is hematite, are added. Here, in the presence of heat, carbon in the first stage the heat in the blast furnace is maintained by pumping in preheated air. In the presence of this heat, carbon in the first stage reacts with oxygen to produce carbon dioxide. This is combustion, and that is why it is exothermic. Enthalpy change is negative. As a result, the temperature rises further and an endothermic reaction takes place in which carbon reacts with the carbon dioxide that can be produced to produce carbon monoxide. This reaction is endothermic. Enthalpy change is positive. Now that the carbon monoxide that had been produced in stage 2 is used in stage 3 as a reducing agent. Carbon monoxide reacts with iron 3 oxide to produce iron plus carbon dioxide. To balance this, this is a gas, this is solid, this is liquid, and this is gas. So that is how iron is produced. Now in stage 4, the calcium carbonate that had been added is decomposed by heat to calcium oxide and carbon dioxide gas. In stage 5, this calcium oxide reacts with the function of the calcium oxide is to remove the impurities. So in stage 5, calcium oxide reacts with the main impurity, that is silicon dioxide, to produce calcium silicate, which is also called slag. Now iron and slag are both molten and in liquid form. That's why they run towards the bottom, but slag, being less dense than iron, floats on top, and iron is collected at the bottom. So iron is tapped out and slag is also tapped out. Now this iron is called cast iron or pig iron because it still has some impurities of carbon left behind. To remove these impurities, this cast iron is taken to a basic oxygen furnace. Here, iron is heated to a temperature of 1500 degrees Celsius to keep it molten, and oxygen is pumped into this molten iron. Oxygen reacts with impurities like carbon to produce oxides, carbon dioxide, sulfur dioxide, etc. These gases escape, leaving the iron pure. However, if there are also some impurities like silicon dioxide, then calcium oxide is also added. Again, calcium oxide reacts with silicon dioxide to produce slag, that is calcium silicate, and slag is removed. That is how route iron is obtained. This is the pure form of iron. Steel is an alloy of iron. There are different types of steel, like low carbon steel. Low carbon steel, as the name states, has less carbon. That is why there are less differences in atomic radii, and thus it is more malleable as the layers can slide past each other. It is used to make car bodies and machinery. High carbon steel is stronger but brittle. It is stronger because due to the atomic difference in atomic radii, the layers cannot slide past each other. This is used in hammers and drills. Then there is stainless steel. Stainless steel is an alloy of iron, nickel, and chromium. This is corrosion resistant and is used in making cutlery and in chemical plants. Next is rusting of iron. Rusting is the corrosion of iron in the presence of water and oxygen. In rusting, iron reacts with oxygen producing iron oxide. Iron oxide chips off and making the metal weaker. Rusting can be prevented by adding a protective layer. For example, paint or grease. Electroplating. And galvanizing. Galvanizing is coating iron with zinc. Rusting can also be prevented by using alloys, because alloys are more resistant to corrosion. One more method is sacrificial protection. In sacrificial protection, a block of a metal which is more reactive than iron is attached to iron. As a result, that metal, for example zinc or magnesium, being more reactive, reacts preferentially to iron, and therefore that metal rusts instead of iron. This is used in underground pipes and bodies of ships.